In this video, we're going to talk about section 7.5, which are trigonometric equations. As we can see, it says, it is now time to solve equations that have trigonometric functions. We can solve these using some algebra or by simply graphing them on our calculators. I'm going to primarily go through the algebra aspect of this. Whenever it comes to the calculators, there is going to be a step-by-step guide on how to use your calculators, but I'm going to use that. I'll let you figure that part of it out and run through that yourself, since that step-by-step guide is pretty straightforward. But we'll get to that here in a couple of minutes. Let's first focus on the algebra portion of it. To solve equations using algebra, you will need to get the equations into factors equal to 0, with each factor containing only one trigonometric function. So here it has a general strategy of how to approach these. And this is just a general strategy for many different kinds of equations that we could be running into. We're going to run into some of those here in the notes, but this is just a general strategy. For number 1, it says get the equation equal to 0. Convert all trigonometric functions into the same function by using identities, or, if that isn't possible, then factor the equation into factors where each has only one type of trigonometric function. So we want to either set the equation equal to 0 or get factors that are equal to 0. Set each factor equal to 0 and solve for the trigonometric function. So we're going to look at each factor individually. And lastly, identify which angles make that equation true. All right. So here, what we're going to have is we're not going to necessarily have factors, but we're going to suppose that here we're dealing with just this equation right here, where this most certainly can just be one factor of a larger equation. So just like we factored other types of equations before, here if we factor the equation, if this ended up being a factor, then we can set this equal to 0 and then solve for theta. But we're just going to start off and say that this is our only portion that we're dealing with. So we have 2 sine of theta minus 1 is equal to 0. We're trying to figure out what theta is equal to. So therefore what we can do is we can take 2 sine of theta and we can bring 1 over to the other side. Since we're solving for theta, then we can divide both sides by 2. And now, using our unit circle, what does theta have to be in order for sine to be equal to 1/2? Well, especially if we're going to focus on from 0 to 2 pi, theta then can be equal to pi over 6 or 5 pi over 6. And now we've solved for the angle that makes this equation true. If we go on to number 2, we have the square root of 3 times the tangent of theta plus 1 is equal to 0. So again, like in number 1 above, we can consider this to be just one factor of a larger equation. However, here we're just given this, so we're just going to consider this to be our entire equation. So again, we're trying to solve for theta. Well, our first step would therefore be to subtract 1 from both sides. Then we're going to divide both sides by the square root of 3. And as usual, we shouldn't have a radical sign in our denominator. So therefore, I'm going to rewrite this as the square root of 3 over 3. Now, when is tangent of theta equal to the negative square root of 3 over 3? Well, that's whenever theta is equal to 2 pi over 3 or 5 pi over 3. Especially if we're going to restrict ourselves from 0 to 2 pi. And again, we're getting these two solutions from our unit circle. And that is something you most certainly should be very comfortable with now at this point in the semester. Alright, if we go on to our next page of notes, we start to talk about how we can do some of this stuff using the calculator. And here it has a very detailed step-by-step guide on how to do this on your calculator. So let's just read through it briefly. It says, however, if equations are more complicated, you may choose to solve them by graphing. So one way is that you can solve these by graphing. More complicated isn't necessarily the only time that you could solve these using graphing or by graphing. You can definitely solve the ones that we did on the previous page by graphing. Obviously, if it's more complicated than that, you can also solve these things using algebra. But another way that you can do this is also solving by graphing if they're more complicated. So what it's not saying here is that if it's more complicated, your only source is to use graphing. But it's saying that whether it's more complicated or not, you also have the additional option of solving these by graphing. And here's two ways that you can do this. If we're trying to solve for a general formula or if we're trying to solve for a specific solution in a given interval. So here, if we just have a general formula or if we have a specific solution that we're looking for in a given interval, we have two different ways that we can do this. Here, if we're trying to solve for a general formula, you would make sure that you set your mode 2 degrees. Then you would find the period and set your x-min and x-max values to 0 and then the period of the trigonometric function that you're dealing with. You would enter the left side of the equation into y1 and the right side of the equation into y2 in your table. And then here find where the two graphs intersect. And then you would convert your answer to radians and add the period times k. We're going to be doing this. We're just going to be doing this using some algebra instead of with your calculator. But this portion right here is what we're going to be doing regardless if we're using the calculator or not. But this is simply just how you could find the solution for a general formula using your calculator. If you have a specific solution on a given interval that you're trying to find, again, you're going to set your mode to degrees. You're going to set your x-min and x-max as the interval values. You're going to enter the left side of the equation to y1 and the right side into y2, just like we had above. You're going to find where the two graphs intersect, just like we had above. And now you're going to convert your answer to radians. But since we're just looking on that certain interval, we don't have to add that period times k to this. Obviously, like we said in a previous section, k has to be an integer. Alright, so what we're going to do now with these next couple of questions is I'm going to show you how to do this with the algebra. I'm going to give you the solutions that you need, and then you can go back and use this step-by-step guide to make sure you can also get these using your calculator. It says, let's try a few using these methods. Determine a general formula or formulas for the solutions to each of the following equations. Then determine a specific solution, if any, on the interval from 0 to 2 pi. So the first thing that it's asking us to do is to use this number 1 right here. And then second is to do the second method right here for a specific solution. So let's take a look at number 3. So just like we did before, we're trying to solve for theta. So therefore, tangent of theta is equal to negative 1. Well, where does tangent of theta equal to negative 1? If we're looking at the interval from 0 to 2 pi, then theta should be equal to 3 pi over 4 or 7 pi over 4. Now, here's something that's really important. For this case, our period is pi. So therefore, one of the things that's important to note is this. I'm going to say note that if we take this first solution right here, 3 pi over 4, and we add the period to it, so you can think of this as adding 1 time the period. So up here we're adding the period times k k is an integer, so right now I'm letting that integer be equal to 1, so we're just adding the period to it. Well, then this is going to be equal to, right, if the period is equal to pi, and you add a pi to this, that's going to end up being 7 pi over 4. Well, 7 pi over 4 is exactly what our second solution is. So therefore, we can say that theta is equal to 3 pi over 4 plus our period times k, where k is an integer. So again, since we're adding the period to it and we're getting our second solution, what we can say then is if we take 3 pi over 4 and then we add our period to it, however many periods we want to have, right, that's what k is as long as k is an integer, we're always going to end up with a solution. And as you can see here, if you would do 11 pi over 4, you would still get that tangent of that theta is equal to negative 1. All right, let's go on to number 4. Again, we're trying to solve for theta. So therefore, what we're going to do is we're going to say that cosine of theta is equal to 0 by subtracting 1 from both sides. Now, on the interval from 0 to 2 pi, when does cosine of theta equal to 0? Well, theta can be equal to pi over 2 or 3 pi over 2. And here we should note that our period is equal to 2 pi. So let's see what that means. Just like we did before, I'm going to say that note that, so I'm going to encroach a little bit on the space on the previous problem. But if we start off with this first solution that we have, and that is pi over 2, if we add the period to it, this is going to end up being 5 pi over 2. Now, if we take the second solution, and which is 3 pi over 2, and we add the period to it, that's going to be 7 pi over 2. Now, let's see exactly what this means, because we're going from pi over 2, then we have 3 pi over 2. We also found out that 5 pi over 2 is a solution, and 7 pi over 2 is a solution. We got to this 5 pi over 2 by adding 2 pi to it, and we got to this 7 pi over 2 by adding 2 pi. Let me write this a little bit differently. We got to this 7 pi over 2 by adding 2 pi to it. All of these are solutions. But what do we see here? To go from our first solution to our second solution, we're adding pi. To go from our second solution to our third solution, we're also adding pi. To go from our third solution to our fourth solution, here we're also adding pi. So the way that we can write this then is that we can say that theta is equal to, we're going to start off on our first solution, pi over 2, and now we can add multiples of pi to this and still end up at a solution. So therefore we can say here that k is an integer. So let me go through this one more time, because it's a little bit different than in number 3. But we found out here that cosine of theta is equal to 0 whenever theta is equal to pi over 2 or 3 pi over 2. Our period is 2 pi, so we should be able to take pi over 2 and add our period to it, and take 3 pi over 2 and add our period to it, and then also end up with solutions, which are 5 pi over 2 and 7 pi over 2. So therefore, we've identified two solutions that are in the interval 0 to 2 pi. But if we go outside of that interval, we can find additional solutions if we keep on going by our period. So therefore, we have all these solutions right here, and we most certainly can continue. But the thing to note here is that we could start off with pi over 2 and add 2 pi, and start with 3 pi over 2 and add 2 pi to get to new solutions. Or we could simply just start off at pi over 2 and keep adding pi to it to keep finding new solutions. So therefore, one way that we can write this is that theta is equal to pi over 2 plus pi times k, where k is an integer. Another way that we could write this, so this right here is simply just using this portion down here to say we can keep adding pi to it. What we could also say is that theta is equals to pi over 2 plus 2 pi k. So now what we're saying then here is that we're going to start off here and we're going to add 2 pi k to end up at a solution. And theta is equal to 3 pi over 2. So we're going to start now here instead and add 2 pi to it. So if we use this approach down here, we're really coming up with two formulas that we have for solutions. However, what we can do is we can combine these two into just one solution formula, because each solution is just pi away from each other. Alright, what we're going to do in the next problem is we're going to see that we're going to have to write it as two solution formulas, because each solution isn't always going to be a certain pi away from the next solution. So let's see what I mean with that on the next page. For number 5, we have 2 sine of 3 times theta plus the square root of 2 is equal to 0. So first off, just like we were doing before, we can say that 2 sine of 3 theta is equal to negative square roots of 2. Then we can say that sine of 3 theta is equal to negative square roots of 2 over 2. So let's leave it here, because this is something that we can identify now on our unit circle. When does the sine of something, right, say that I wanted to rewrite this as the sine of x is equal to negative square roots of 2 over 2? Well, what does x have to be in order for our solution to be negative square roots of 2 over 2? Well, we would have to have it equal to 5 pi over 4 or 7 pi over 4. So x would have to be equal to this. And obviously now I simply just substituted in x for 3 theta. So therefore I'm just going to say that 3 theta has to be equal to this. Alright, so now the important thing to realize here is this. Just like we did on the previous page, I'm going to say that note that if we take 5 pi over 4 and we add our period to it, again, what's our period for the sine function? Here our period is 2 pi. If we add the period to this, we're going to get 13 pi over 4. If we take 7 pi over 4 and we add the period to it, we're going to get that it's 15 pi over 4. which means now that if we go from 5 pi over 4, our next solution is 7 pi over 4. Our next solution after that is 13 pi over 4. And our next solution after that is 15 pi over 4. Right? We got to from this one to this one by adding 2 pi. And we got from this one right here to this one over here by adding 2 pi. We cannot simply just take 5 pi over 4 and add pi to it. If we take 5 pi over 4 and add pi to it, we're going to be at 9 pi over 4. And if we take 7 pi over 4 and add pi to it, we're going to have 11 pi over 4. However, these two things are not solutions. So we can't simply just take these things like we did in the previous problem and add pi to it in order to get to our next solution. So therefore, what we're going to have to say is that theta, I'm going to say that 3 theta for now, 3 theta is equal to 5 pi over 4 plus 2 pi k, or 3 theta is equal to 7 pi over 4 plus 2 pi k. And obviously I'm going to say here where k is integer. But let's go ahead and solve this for theta. So therefore we're going to say that theta is equals to 5 pi over 12 plus 2/3 pi k, or theta is equals to 7 pi over 12 plus 2 pi k over 3. So I'm just dividing everything by 3 to solve exactly for theta. So this one was a little bit different. Here we have to have our solution in the form of 2 solution formulas. We cannot combine these into just one solution formula the way that we did in number 4 above. Alright, let's go on to number 6. Here we have that the cosine squared of theta is equal to the sine of theta times the cosine of theta. So the first thing to realize here is that cosine squared of theta is simply just cosine of theta times the cosine of theta. So I just rewrote the left-hand side of our formula as a product of 2 cosines. The right-hand side of our formula is the sine of theta times the cosine of theta. Now, if the left-hand side must equal the right-hand side, what do we know must be true? Well, it must be true that cosine of theta is equal to the sine of theta. Because both of these were just multiplying by the cosine of theta. So therefore, if we're both just multiplying them by the cosine of theta, then the cosine of theta must be equal to the sine of theta. So we can say that here, sine of theta must equal cosine of theta. Now, where does the sine of theta equal to the cosine of theta? So therefore, we're going to say that these two things are equal when theta is equal to pi over 4 or 5 pi over 4 on the interval that we're looking at from 0 to 2 pi. So here what we can see is that we can keep adding pi to this. So we can say that theta is going to be equal to pi over 4, which is our first solution, plus pi times k, right? If you add pi to this, you're going to end up at 5 pi over 4. Again, where k is an integer. Alright, so here's a couple of examples that we went through then. For the first example in number 3, we had a relatively straightforward example where we're solving for theta. Then we can add the period to our first solution and end up at our second solution, and really at any solution after that, even if we want to go past 2 pi. In the second equation, we again solve for theta, and then we notice that we can add just half of the period to this first solution to end up at all of the rest of the solutions. Since here, by adding the entire period to it, we would always skip a solution that was only half the period away. In the third example that we did, but it was number 5, we again just solved for what we were taking the trig function of. Here it's 3 theta instead of just theta. But we then notice that we can't just add the period or half of the period to our first solution to end up at the other solutions, since we're skipping some solutions in between, or some numbers in between that aren't solutions. So therefore we had to come up with 2 solution formulas. And lastly here, it was simply just identifying that exactly what are we working with on the left-hand side and what do we have on the right-hand side, to realize that's one of those factors of each side, therefore must be equal. And then we can identify the solutions on the interval from 0 to 2 pi, but also then a general solution formula. Alright, that concludes section 7.5, because the next problems are the practice problems, but as usual, those are left for you. That concludes this lecture video.